Look outside right now. Whatever you see, trees catching light, clouds drifting, a city humming with traffic, maybe just a window in the ordinary world beyond it. All of it is part of a system that has been slowly, quietly winding down since before the first human being ever drew breath. This isn't poetry, it's physics. The sun, the same star that rose this morning and will set tonight, is not the stable, eternal fixture we treat it as. It is a furnace burning through its own fuel, and like any furnace, it is changing. Right now, at this very moment, the sun is about 10% brighter than it was when life first appeared on Earth. 10%. That might not sound like much, until you realize that a change of just a few percent in solar output is enough to boil oceans or freeze continents. Life on this planet has survived so far, partly because the Earth itself adapted, shifting its chemistry, its atmosphere, its feedback loops, buying time in ways that feel almost impossibly fortunate. But the adaptations are not infinite. The margin is shrinking. The oceans, which cover most of this planet and regulate its temperature and harbor the base of nearly every food chain, are not permanent. The sky above them, the thin blue film that makes Earth look alive from space, is not guaranteed. The forest pulling carbon from the air, the ice reflecting sunlight back into space, the intricate biological machinery that makes a blade of grass possible. All of it exists inside a window that opened, and a window that will close. What makes this hard to feel, genuinely feel, not just intellectually acknowledge, is that the dying is slow. Not slow like a season, slow like geology. Slow in a way that makes a human lifetime feel like a single frame in a film that runs for billions of years. The changes accumulating right now, today, won't be visible in your lifetime or your children's or the 10,000 generations after them. And so the mind does what minds do with things too large to hold. It lets them go. But the story is happening whether we hold it or not. And here is where it gets strange. Because 5 billion years sounds like a number so large it becomes meaningless, an abstraction, a nothing word dressed up in zeros. It isn't 5 billion years. Say it out loud and it almost sounds made up. It's the kind of number that slides off the brain without leaving a mark. Too big to picture, too distant to feel real. We hear it and nod politely, the way you nod when someone explains how far away a star is. Sure, a lot. Got it. But here's the thing about enormous timescales. They have a way of collapsing when you start pulling on the right threads. Think about it this way. 1 billion years ago, there was no grass on Earth, no flowers, no insects. The land was barren rock and thin air, and the oceans were full of things too simple to have names we'd recognize. That was 1 billion years ago, and the planet has transformed so completely since then that an alien visiting both versions of Earth might not believe they were looking at the same world. Now multiply that by 5. 5 billion years is enough time for continents to not just drift, but fully rearrange themselves, again and again and again. It's enough time for species to rise, dominate, go extinct, and be replaced by things evolution hasn't even sketched yet. It's enough time for oceans to change chemistry, for mountain ranges to be born and ground back down to plains, for the atmosphere to be rewritten from scratch. And somewhere inside that vast corridor of time, Earth's story ends. Not with a sudden catastrophe, not with a single dramatic moment you could point to on a timeline. More like a sentence that gets harder and harder to read until the ink finally runs out. What makes this feel closer than it should, what makes 5 billion years stop feeling like an abstraction, is realizing that the clock isn't somewhere out in space, anonymous and indifferent. The clock is the sun, the thing that rose this morning, the thing warming your skin right now. It has been counting down since before the Earth existed, and it has already used nearly half its fuel, which raises a question worth sitting with. What exactly is the sun burning? And what happens when it starts to run out? The star at the center of our solar system feels permanent. It rises every morning, powers every living thing, and has been doing exactly that for so long that permanence seems baked into its nature. But the sun is not permanent. It is a machine, and like every machine, it runs on fuel. Right now, deep inside the sun's core, hydrogen atoms are being crushed together under unimaginable pressure and heat, fusing into helium, releasing energy in the process. This is nuclear fusion, and it is the only reason the sun shines. Every second, the sun converts roughly 600 million tons of hydrogen into helium. Every single second. That number sounds inexhaustible. It isn't. The sun has been burning through its hydrogen supply for about 6 billion years. It started with enough to last approximately 10 billion years total. Do the math, and you'll find something quietly unsettling. We are almost exactly at the halfway point. The sun is middle-aged, and middle age for a star comes with consequences. Here's what most people don't realize. The sun isn't static even now. It's been gradually brightening since it was born, slowly, imperceptibly by human standards, but measurably. It's already about 30% more luminous than it was when Earth formed. And it will keep brightening as the core contracts, temperatures rise, and fusion accelerates. The sun is not waiting for some distant deadline to start changing. It has been changing the whole time. We just haven't been around long enough to notice. The real transformation, though, begins when the hydrogen in the core finally runs out. At that point, the sun's internal balance, the constant tug of war between gravity pulling inward and radiation pushing outward, breaks down. Gravity wins temporarily. The core collapses and heats up. But that heat reignites fusion in a shell surrounding the core. And that shell burns so intensely that the outer layers of the sun begin to expand. Slowly at first, then dramatically. The sun swells into what astronomers call a red giant. Its surface, once compact and blazing white-hot, cools and reddens as it stretches outward, past Mercury, past Venus, possibly reaching all the way to where Earth now orbits. The star that once fit comfortably in our sky will become the sky. But long before that final expansion, long before the sun physically engulfs anything, the damage has already begun. Because a brightening star doesn't need to swallow a planet to destroy it. Heat alone is enough. And that's exactly where we're headed next. The sun doesn't announce its changes. There's no sudden flash, no warning signal beamed down to Earth. It happens slowly. So slowly that any civilization watching would need instruments far beyond anything we have today just to notice the trend. But the trend is merciless. As the sun burns through its hydrogen fuel over the next billion years, it grows steadily brighter. Not dramatically, not all at once, just a fraction of a percent per million years. That sounds harmless until you do the math and realize that even a 10% increase in solar output, which is coming, is enough to fundamentally rewrite the chemistry of an entire planet. It starts with the water cycle breaking. Right now, Earth exists in a kind of thermal negotiation. Heat comes in, heat goes out, and the oceans hold the balance. But as the sun intensifies, that negotiation tips. More energy arrives than can escape. The oceans begin absorbing more heat than they release. Surface temperatures creep upward. Not like summer, but permanently, irreversibly, degree by degree across centuries. The first thing you'd notice, if you were there, is the clouds. They change. The low-level clouds that currently reflect sunlight back into space, Earth's own natural shield, become unstable. Climate models suggest there's a threshold, somewhere around 250 million years from now, where those clouds collapse entirely. And when they do, it's not a gradual warming anymore. It's a runaway. Think of a pot on a stove. For a long time, nothing seems to happen. Then everything happens at once. Water evaporates faster than it can return. Vapor rises into the atmosphere. And here's the part that makes this process so catastrophically self-reinforcing. Water vapor is itself a greenhouse gas. Every bit of evaporation traps more heat, which drives more evaporation, which traps more heat. The feedback loop locks in and accelerates. The oceans don't just warm, they begin to go. Not all at once. The shallows first, the coasts, the warm equatorial seas. Then the great depths, those cold, dark basins that have held water since before complex life existed. The pressure and temperature rise together until the ocean surface reaches a point where liquid water simply cannot remain stable under open sky. It boils, not in the violent, dramatic sense of a kettle, but in the planetary sense, where the boundary between ocean and atmosphere dissolves and the water migrates upward, molecule by molecule, into a dense, scalding vapor layer wrapped around the world. The sky would turn white, not with clouds but with steam, a permanent thickening shroud of superheated water vapor pressing down on a surface that no longer has any ocean left to speak of. Atmospheric pressure would spike. Temperatures on the ground would climb past the boiling point of water, past 200 degrees, past 300, still rising. Earth would begin to look, in its death, remarkably like Venus looks today. Venus, our nearest neighbor, a planet that may once have had oceans of its own. There's a certain weight in that comparison, the idea that what we're describing for Earth's future might be Venus's forgotten past. A world that crossed the same threshold, lost the same battle, and has been a testament to it ever since. The oceans are gone. The sky is poisoned with their remnants. The surface is bare rock, cooking under a sun that is only going to keep growing. And yet, and this is where the story refuses to end simply, the question that follows is not about water or temperature or atmospheric chemistry. It's about life. Because life on Earth has survived asteroid impacts, mass extinctions, volcanic winters, and deep freezes that turned the entire planet to ice. Life is not fragile in the way we tend to assume. It's stubborn. It's inventive. It finds corners. So the real question, the one that comes next, is whether anything, anywhere on this scorched and waterless world could still be holding on. The oceans are gone. The sky is a furnace. Everything we ever called home has been reduced to bare, scorched rock, baking under a sun that barely resembles the one that nurtured life for billions of years. And here's the question that refuses to go away. Is anything still alive? The answer, against all odds, might be yes. Just not life as we imagine it. Deep underground, kilometers below the surface, something extraordinary may still be clinging on. Microbial life, the kind that exists in total darkness, feeding off chemical reactions in rock, completely indifferent to sunlight, has already proven it can survive conditions that would destroy everything else. We know this because we find it here, right now, buried in the crust of our own planet. These organisms don't need the surface. They don't need the oceans. They live in a world of their own, slow and ancient, where a single generation might span thousands of years. As the surface temperature climbs past the point where lead melts, these deep communities would feel only a gradual warming. A pressure, a slow tightening of the conditions they've managed to endure for eons. Some would die, but the deepest, the most resilient, they might hold on longer than anything in the history of complex life. There's something quietly devastating about that image. The last living things on Earth, invisible, nameless, buried in stone, completely unaware that they are the final chapter of a 4 billion year story. But even they have a limit. Heat conducts through rock. The crust itself begins to behave differently as the planet's surface temperature equalizes with its depths. The thermal refuge shrinks. Centimeter by centimeter, the zone where liquid water can still exist, even trapped in microscopic pores within the rock, retreats deeper, then disappears entirely. And then there is nothing. No metabolism, no reproduction, no chemistry reaching toward complexity. The last biological process on Earth ends not with a dramatic extinction event, not with an asteroid or a plague, but with a quiet threshold crossed somewhere in the dark, somewhere no one will ever witness. Life's story on this planet will have lasted roughly 5 billion years from its first fragile spark to its final ember. That is not a tragedy. That is almost incomprehensibly long. But it will end. What comes next doesn't care about endings. The sun has its own logic now, its own momentum, And what it does next makes everything we've described look like a prelude. The sun has been patient. For billions of years, it burns steadily, reliably, almost gently, the kind of star that lets life flourish on a rocky planet nearby. But patience has a limit, and when hydrogen fuel in the core finally runs out, everything changes at once. What happens next is not a slow fade. It's a transformation so violent, so complete, that the word expansion barely captures it. The sun begins to swell, not gradually the way we imagine a balloon filling with air, but in pulses, in lurches, growing and contracting and growing again, each cycle larger than the last. Over a few 100 million years, it expands to 100 times its current size, then 150, then 200. The light it casts stops being the warm yellow we know and shifts into something deeper, something red and enormous and ancient looking, flooding what's left of the inner solar system in a permanent copper dusk. Mercury disappears first, then Venus. Both swallowed cleanly, their orbits consumed before they even have time to drift. And then comes Earth's turn. By this point, Earth is already unrecognizable. The oceans are gone. The atmosphere has long since been stripped away. The surface is bare rock, scorched and cracked, a world that has been dying for hundreds of millions of years before this final moment arrives. But there is still a moment, a last one. As the outer edge of the sun reaches Earth's orbit, the planet doesn't explode dramatically. It doesn't shatter. It simply enters. It crosses the threshold into the solar atmosphere, a region so hot, so dense with plasma and radiation, that rock behaves like vapor. The crust begins to dissolve. The mantle follows. Layer by layer, everything that was ever Earth gets absorbed, broken down into its most basic elements, scattered through the body of a dying star. There's a strange intimacy in that. The iron at Earth's core, the same iron that once flowed through every living thing that ever existed on this planet, becomes part of the sun, the silicon, the carbon, the oxygen, all of it reclaimed. In a way, the sun takes back what it helped create billions of years earlier, when its own gravity gathered dust and built the planets that circle it. No explosion, no final scream. Just dissolution, quiet and total, into something far older and larger than anything Earth ever was. But the story doesn't end there. Because what the sun leaves behind after it finishes burning, after it finishes swallowing and collapsing and fading, is something worth looking at closely. So the red giant has come and gone in its fury. But what does it leave behind? Here's where most people assume the story just ends. Darkness, silence, nothing. But that's not quite right. And the truth is stranger than the ending most people imagine. When a star expands and engulfs a planet, it doesn't simply erase it cleanly. The process is violent and messy in ways that unfold over millions of years. Earth, as it spirals inward through the outer layers of the bloated sun, would be subjected to forces that pull it apart long before it reaches anything resembling a core. Tidal forces, plasma drag. Temperatures that don't just melt rock, they unmake it at the atomic level. What was once a world of oceans and mountains and living things becomes a diffuse cloud of vaporized minerals, metals and gases, slowly mixed into the body of the star itself. Earth wouldn't be swallowed whole, it would be dissolved. And yet, those atoms don't disappear. Iron, carbon, calcium, oxygen, every element that ever made up a mountain, a bone, a raindrop, it becomes part of the sun's outer envelope, drifting through that vast stellar atmosphere. In a strange, almost poetic sense, Earth doesn't die, it merges. Some of that material gets ejected. As the red giant pulses and sheds its outer layers into space, it's possible, genuinely possible, that particles which were once part of Earth's crust get carried outward into the galaxy, scattered, set adrift across light years, over billions of years, to eventually fall into new clouds of gas and dust, to seed future solar systems, to become perhaps parts of planets we can't yet imagine. The remains of Earth don't sit still, they travel. And what's left of the sun after all of this, after the giant phase burns out, after the outer shells disperse, is something extraordinary, something quiet and dense, and almost impossibly beautiful. The Earth is gone, but the sun is not finished yet. What happens to a star when it finally runs out of fuel is one of the most staggering spectacles the universe has to offer. And our sun, for all its ordinary size and quiet reliability, will go out in a way that is genuinely, heartbreakingly beautiful. After swallowing whatever remains of the inner solar system, the sun begins to lose its grip. The outer layers, vast shells of gas glowing with oxygen and hydrogen, start drifting away into space. Not violently, slowly, almost gracefully, they expand outward in every direction, forming what astronomers call a planetary nebula, though it has nothing to do with planets. The name is just a relic of old telescopes that couldn't quite resolve what they were seeing. What they were actually seeing was a dying star exhaling. And that exhalation is extraordinary. The gas doesn't simply vanish. It catches the ultraviolet light pouring from the collapsing core and begins to glow. Blues, greens, deep crimsons, rings within rings. Some planetary nebulae look like cosmic eyes staring back at you. Others resemble hourglasses or butterflies or soap bubbles impossibly suspended in the dark. The universe, in this moment, is making art out of destruction. Our sun will produce something like this, its own luminous farewell, drifting outward across thousands of light years, visible to any civilization patient enough to be watching. For tens of thousands of years, that glowing shell will be the most beautiful thing in this corner of the galaxy. But beauty doesn't last. The gas keeps expanding, keeps thinning, until eventually it disperses entirely into the interstellar medium, recycled, absorbed, maybe one day folded into a new star, a new planet, something that doesn't exist yet. The matter that was once the sun becomes raw material for futures we cannot imagine. And left behind, at the center of all that fading light, is something very small, very dense, and completely alone. What's left isn't nothing. That's the strange part. After all that fury, the swelling, the shedding, the final exhale of light, what remains is a white dwarf. A dense, silent ember, about the size of Earth, but with the mass of a star still packed inside it. No fusion, no burning, just heat, slowly leaking out into a universe that grows colder and emptier by the billion years. And here's what makes it genuinely eerie. It's stable. It won't explode. It won't collapse further. It will simply cool. For trillions of years, far longer than the universe has even existed so far, this object will radiate its stored heat in perfect, indifferent silence, dimming from white to yellow to a faint and sullen orange. Eventually, in timescales so vast they have no human equivalent, it becomes what physicists call a black dwarf. A cold, dark, inert sphere drifting through space. Invisible, undetectable, gone in every meaningful sense except mass. But right now, in that long intermediate phase, the white dwarf still glows faintly. And if you could somehow stand in what was once the outer solar system, you would see it, a dim blue-white point of light, not warm enough to notice, not bright enough to cast a shadow. Just there, a gravestone that radiates. The planets are gone or dispersed. The comets have long since been flung into interstellar space. Whatever remained of the asteroid belt drifted away when the sun expanded. The solar system, as a system, doesn't really exist anymore. What exists is a solitary object in an increasingly lonely universe, with no one to witness it cooling down. That thought tends to sit heavy. An entire star, our star, reduced to something smaller than the world we live on, quietly fading across timescales that make civilization feel like a spark from a struck match. But here's the question that changes everything. Does it have to end this way for us? The white dwarf is the sun's fate. It doesn't have to be ours. Because long before any of this happens, long before the first red giant stages even begin, the only variable that could rewrite this story entirely isn't physics. It's us. So here we are. A red giant has swallowed the Earth. The sun has collapsed into a cold, dim ember. Everything we know, every city, every mountain, every record of human thought, would be gone unless we left before any of it happened. The question isn't absurd. It's actually one of the most serious questions in long-term science and philosophy. Could humanity, given enough time, escape its own solar system entirely? The honest answer is that 5 billion years is an almost incomprehensible runway. To put it in perspective, 5 billion years ago, the Earth didn't exist. Complex life didn't exist. The entire history of everything you've ever read about, civilizations, extinctions, ice ages, the dinosaurs, fits inside a fraction of the time we have before the sun becomes dangerous. If we survive the next few centuries, the next few thousand years, the trajectory of what becomes possible stretches so far into the future that the word escape barely captures the scale of it. Physicists and futurists have mapped what a technologically advancing civilization might look like across enormous timescales. The framework, loosely, moves through stages. First, mastery of a planet, then mastery of a solar system, then, eventually, the ability to reach beyond it. None of these transitions are guaranteed, but none are forbidden by physics either. That distinction matters. The nearest star system, Alpha Centauri, sits about 4 light-years away. With current technology, reaching it would take tens of thousands of years. But current technology is not the ceiling, it's the floor. Even conservative projections suggest that within centuries, not millennia, propulsion methods like laser sails, nuclear pulse drives, or technologies we haven't yet named could reduce that journey to something between a few decades and a few centuries. Lifetimes, not geological ages. And the sun gives us warning. It doesn't ambush us. The slow brightening begins hundreds of millions of years from now. The oceans don't boil overnight. The timeline is staggered, almost deliberately, as if the universe built in a long, slow alarm clock, giving life time to respond if it's paying attention. What would escape actually look like? Not a single heroic moment. It would be incremental, generational, distributed. Small populations settling around other stars. Cultures diverging over thousands of years into forms we couldn't recognize. The concept of humanity itself becoming something more like a family of civilizations spread across dozens of star systems, each adapting, each evolving. The species that leaves might not be biological in the way we understand. The descendants that arrive might be something the people who launched the ships could never fully imagine. There's something quietly staggering about this possibility, not because it's certain, but because it's genuinely open. The physics doesn't close the door. The timescale doesn't close the door. What closes doors, historically, has always been something internal. Conflict, short-sightedness, the failure to take seriously what lies far ahead. And that's where this stops being astronomy and starts being something more uncomfortable. Because the question of whether humanity escapes the solar system in 5 billion years is, at its root, a question about who we choose to be in the next 500. The long survival requires a thread of continuity that reaches back to decisions made right now, in the only moment any of us actually inhabit. The stars aren't waiting. They don't care either way. But the fact that the path exists, that it is physically real, mathematically possible, written into the same laws of nature that will eventually destroy this world, that is not a small thing. And what that possibility reveals, when you hold it alongside the full 5 billion year timeline, is something that reframes not just the future, but everything we think we understand about where we stand right now. There's a particular kind of vertigo that comes from standing at the edge of something enormous and truly looking down. We've traced the full arc now, from the sun's slow brightening to the scorching of the oceans, to the swallowing of the inner planets, to the long, cold silence that follows. And if you step back far enough to see that entire timeline at once, something unexpected happens. It stops feeling like a story about endings. It starts feeling like a story about scale and about what we are inside of it. Here's what strikes me most. The Earth formed roughly 4 or 5 billion years ago. Complex life, the kind with eyes and nervous systems, and the ability to wonder about its own existence, appeared in only the last 600 million years or so. Human civilization, everything we call history, every empire and invention and idea, fits inside the last 12,000 years. Which means that against the remaining 5 billion years the Sun still has to offer, our entire recorded story so far is less than a single breath. That's not meant to be crushing. It's actually the opposite of crushing, if you let it land properly. Because what it means is that we are extraordinarily early. Not late. Not at the peak. Early. We are, in cosmic terms, something like a species that has just learned to stand upright. The universe is not winding down around us. It is, from any honest perspective, barely underway. And yet here we are, conscious of all of it. That asymmetry is strange and worth sitting with. The stars don't know they're burning. The planets don't know they're drifting. But something on this particular rock, orbiting this particular star, in this particular unremarkable corner of a galaxy, among hundreds of billions of galaxies, something here looked up and started asking questions. That's not nothing. In fact, given everything we've mapped out, it might be the most remarkable thing in the entire timeline. What the arc from now to 5 billion years really reveals is that existence on cosmic scales isn't defined by permanence. Nothing is permanent. Not stars, not solar systems, not galaxies themselves. The universe is not a stable backdrop against which life briefly flickers. It's a process, violent, creative, constantly converting one form of order into another. Life is part of that process, not a footnote to it. Which brings us to a question the timeline quietly forces onto us. Not in some abstract philosophical way, but with genuine weight. If we know the clock, if we can see the arc, if we understand where we sit inside this vast unfolding story, what exactly do we do with that knowledge? What does it demand of us? That question doesn't disappear just because the deadline is 5 billion years away. If anything, the scale makes it more urgent, not less. 5 billion years is so vast it almost protects you from feeling it. The numbers are too big, the timeline too remote. It's easy to nod along, file it somewhere in the back of your mind under "Not my problem," and move on with your Tuesday. But here's what I can't stop thinking about. Every civilization that ever rose on this planet, every empire, every library, every song someone sang to their child at night, existed in a thin sliver of time that the universe didn't have to give us. The sun didn't owe us stability. Earth didn't owe us oceans. And yet, here we are, conscious, curious, and somehow aware that the clock is running. That awareness is not a burden. It's the most extraordinary thing about us. No mountain knows it will erode. No star knows it will expand. But we know. And that changes everything. Not about the timeline, but about what we choose to do inside it. The question was never really what happens in 5 billion years. The real question is what you do with the years you actually have, the ones that are yours. Because the sun will enter its red giant phase whether we waste our time or spend it well. The difference is entirely ours to make. There's something quietly liberating in that. When you zoom out far enough, the smallness of our conflicts becomes almost funny. And the things that actually matter, connection, discovery, the impulse to build something worth building, those things shine a little brighter against the dark. This is what the universe does when you really look at it. It doesn't crush you with its scale. It clarifies. It strips away the noise and leaves you with a strange, steady sense of what's worth carrying forward. The clock is ticking. It always has been. But right now, in this moment, you're here, aware, alive, part of a species that looked up at the sky and refused to stop asking questions. That's not nothing. That's everything. If this video made you think, made you feel something you hadn't quite put into words before, Then do something small but meaningful right now. Subscribe so you don't miss what's coming next. Leave a like if this journey was worth your time, and drop a comment below. Tell me, when you think about the end of everything, what thought does it leave you with? I read every single one, and I'll see you in the next one.